Hello, am I audible? Hello, am I audible?
Yes, sir.
So someone has to say that. How could I come to know? Why are you waiting for other side? Never understand this. Is the screen visible?
Yes, sir.
Yes. Let's see to this part. Okay, so in the last lecture we had seen up to this part and we discussed about the, let's say, boiling process. So starting from point 1, so that is both the phases, both the components are liquid. Then 1 to 2, that is heating, so that is sensible heat addition. Then 2 onwards, it is the boiling point of one component. So that particular component starts its phase change, whereas the other component is free. It is still in the liquid zone or vapor zone, whatever it is, and as such, that is a sensible one. So 2 to 5, there is a temperature rise. That is because the other component is absorbing the sensible heat. The first component is absorbing the latent heat. So there is a phase change between 2 to 5 for component A. And this is the same one whose concentration you are measuring. So concentration X, that is, let's say, of ammonia, then ammonia is getting the phase change. Okay. 5 onwards, that is also in the vapor phase. So let's say superheated part. Now if you reverse the same process, you will get the condensation. So vertically upward, I will say boiling. Vertically downward, I will say condensation. Okay. Now you repeat the same experiment at different values of the concentration. So right now here I'm saying that, let's say this is some x1 value. Okay, in the chart as you can see over here. Let's say x2, x3, x4, x5, x6, x7, x8, blah blah blah. Then this point 2 will be, say, let's say 2 dash, 2 double dash, 2 double triple dash, 2 quadruple dash, and like that. Fine. So what you actually observe with different concentration values is this red color locus and this black color locus. Do you agree? Provided that this entire transformation is taking place at different concentrations, but the pressure is same. Do you agree? Any doubt to anyone?
No, sir.
So what you get over here is a red color locus for different concentration at the start of the boiling. So we call this as boiling line. And the end of the boiling, or in the reverse way, it is the start of the condensation. So we call the black line as the condensation line. Fine. How you get these two lines? By changing the concentration only. Pressure is same. So you get one locus for one particular pressure. Now you change the pressure. So what you get at one particular pressure, as I said, equilibrium boiling line, equilibrium condensation. At one particular pressure, let's say P1. Now you change this. At different pressures, you get different loci. Fine. So there are, let's say, 3 pressures: P1, P2, P3. P3 is highest, P2 intermediate, P1 lower. Naturally, lower pressure होगा तो lower temperature, higher pressure होगा तो higher temperature. Quite obvious. So that is why the upper loop is for the higher pressure, lower loop for the lower, the middle one is the intermediate. So now I got 3 red lines, 3 black lines. Any doubt to anyone? 3 condensing lines means equilibrium condensation lines and 3 equilibrium boiling lines. Red. Any doubt to anyone?
No, sir.
When you vary the concentration, you will get one loop. When you change the pressure, you get different loops. Clear? Any doubt? Any doubt to anyone in the class?
No, sir.
It's online class.
Yeah.
They are in front of me. I can read their face. Or the online people only. Now you reverse the direction, as I had said. So for the same concentration, you will retrieve the same path. Fine. And instead of 1 to 6 in the upward direction, now I have written 1 to 6 in the downward direction. Or you can say 6 to 1 in the downward direction. Doesn't matter. Basically, it would be the reverse process, so that is condensation. Nomenclature can be anything. Fine. So you are entitled to get the same loci, one for the condensation line, start of condensation, the other at the end of the condensation, which in the reverse way would be the start of the boiling and the end of the boiling. So even if you reverse the process, the points 2 and 5, whether it is boiling, 2 becomes 5, 5 becomes 2. But the points would be same, unique, for a given pressure, for a given concentration. Do you agree with this? Listen carefully, every statement, every word. For a given concentration, 2 and 5 same. Whether you go in the forward direction, that is boiling, or reverse direction, that is condensation. 5 का 2 होगा, 2 का 5 होगा. But the points are same. Correct? You change the concentration, you will get one red locus, one black locus. Right? 2 loci. The red locus, we call it as equilibrium boiling line. Black locus, we call it as equilibrium condensation. And this is for one particular pressure. You change the pressure, you will get this loop for the multiple pressures. So multiple loops for multiple pressures. Fine.
So this particular thing with the mixture that is happening because of different
Concentrations.
So this does not happen with our air because
It happens. Yes.
because there is moisture and air together and
No. If you are talking about air, then whether dry air or moisture. If you consider dry air, it is a homogeneous mixture.
yes,
You can separate oxygen and nitrogen. Boiling points are different.
yes, I am talking about dry
If you consider
plus-
moist air,
yes, moisture.
then you can separate it very easily.
So
Condensation.
this particular thing happens with air also.
Why not? It is a homogeneous mixture. You can separate them. If the atmospheric pressure is different, the points would be different. Because your concentration also changes. How much moisture it na? Right?
So the thing which we were talking about yesterday, that when the two components of the mixture mix, either they will expand or they will contract.
Mhm.
That also happens with air and water.
How you will reduce the temperature? Heat transfer will be. You have to reject it.
Because writing enthalpy of the air, we only consider the enthalpy of the Cp of air and then Cp of water, which we were doing yesterday, and plus we were adding some delta X also yesterday, right? Plus or minus. We do not consider that for air, right?
Because for the air it is very, very negligible. How much heat transfer or the change in that enthalpy, how much it is, if it in comparison with the air enthalpy and let's say water enthalpy, if your delta H is 0.1, it only depends on the constituents. Okay, any other doubt to anyone from the class, online class?
No, sir.
Yes or no? Okay. Now the only point remaining is 3 and 4. उसके बारे में कुछ discuss नहीं किया. So now pay the attention with respect to the figure. Let's say I start the evaporation from here. Okay. Condensation के बजाय boiling. Let me go to that figure. Let's see over here. This is entirely liquid, and as you reach point 2, let's say component 1 whose concentration is mentioned over here starts boiling. Now this is a mixture, correct? One component of which starts boiling. Now when you let's say you add some heat, okay, let it reach over here or here or here, so I assume it over here. Now how you will find the concentration? Because now you have the concentration of the liquid phase, concentration of the vapor phase.
Sir, lever rule.
Lever rule. So that is why these 2 points will give you the concentrations in the opposite sense. Since this is related to the liquid part from, let's say this, इसको क्या बोलेंगे, कुछ नाम बोलो इसका point. Let's say some x point. So x3 and 4,3. Okay, that ratio will give me the vapor concentration. And x4 divided by 3,4 total will give me the liquid concentration. Now why this liquid, or rather how this liquid and vapor? So common sense, you start from point 2. You add some heat, इतना सा vapor है, बाकी पूरा liquid. You reach to 0.5, just below 0.5. तो क्या होगा, इतना सा liquid बचा, बाकी सब vapor. So it is always in the opposite direction, opposite sense. So you move anywhere between 2 and 5. On this side it will be vapor, on this side it will be liquid. Do you agree or not? I add some heat after 2. Let's say over here. Then this small distance is vapor part. Baki sab liquid. You reach towards the what you call saturation. Then the entire part will be vapor. Very small amount left for liquid. So this is always vapor part. This is always liquid part. Do you agree? Any doubt to anyone? इस पे हम लोग को न्यूमेरिकल सॉल्व करने हैं. So if you are not clear with this, no one can help you.
Yes, sir.
So the conclusions which we discussed a little bit yesterday also. A binary mixture, any mixture basically, binary, ternary, quaternary, minimum binary. Binary mixture does not have a unique boiling point. Since it is a homogeneous mixture, since it is a miscible one over the at least the given range in which I want to operate it as a refrigeration circuit, then at one particular value of the concentration and the pressure, one particular component will start boiling, whereas the other is still able to absorb the heat in the sensible way. One is absorbing the heat in the latent way, phase change. The other is free to absorb the heat in the sensible way. So there is no unique boiling point. Do you agree?
So the rule is applied manually. How is the mixture is vapor and how much is the
Mass.
sorry mass is vapor and how much is it will not
And read the concentration. Lever rule length will give you mass. Concentration directly niche.
so for example that example we are applying liver so
Let's say I'm here.
yes,
So how much is the vapor mass? Is ये छोटा सा इतना convert हो गया. Remaining mass
so the
liquid.
vapor mass will contain both the constituents, right?
Yes. So this will be my vapor concentration. This will be my liquid concentration.
The mass will be the concentration.
Nothing. Mass and concentration. क्या लेना देना? Concentration of ammonia is this. Concentration of ammonia vapor 0.3 related. Concentration of ammonia liquid 4. Total मिला के बीच में.
So the vapor will contain इतना ammonia का vapor and 3 point से जो concentration रहेगा वो vapor में उतना ammonia रहेगा.
See, this is my same concentration as of 2 and as of 5. Why it would change? What is changing is only the phase. So vapor phase concentration whatever x3, liquid phase concentration x4, finally फिर से 5. Start at 2, 3 and 4 eventually मतलब 3 इस तरफ जाएगा, 4 यहाँ से 5 की तरफ आएगा, and eventually end up at 5 only. And we will say that one component entirely got converted into the vapor. Second may be liquid, second may be vapor. Depends. It depends on its temperature. Fine. So lever rule, the length will give you the ratio of the masses. Liquid mass and vapor mass. Liquid concentration and vapor concentration would be corresponding to x3 and x4. x3 is vapor. Come. 4 also eventually both will reduce because एक left के तरफ जाने वाला है, दूसरा भी left में जाएगा. That is 0.4, but that is on the right hand side of what I can say the actual line. So both points 3 and 4 will be eventually moving towards the left hand. Both will be reducing. And finally, I end up at the same x5. और इसका क्या होगा? 3 will become somewhere 0 or whatever minimum part, and entire vapor part, that is x5. So eventually vapor x5 is the same as that same concentration. x1, x2, x5 same. It is just the liquid and the vapor which is changing. Phase change. Total ammonia same. Liquid में हो या vapor में हो. Ammonia liquid, ammonia vapor. Ammonia vapor 3, ammonia liquid 4, total ammonia 2,5, same. Clear? Any doubt? Lever rule for mass.
Total कितना vapor है?
Mass of vapor, mass of liquid. For that lever rule. Let's say that intermediate point को कुछ बोलते x. तो 3x divided by 3,4, that is vapor, and 4x divided by 3,4, that is liquid. eventually X4 will reduce, मतलब liquid reduce, and X3 goes on increasing.
बेसिकली वो उतना वो आइडिया नहीं देता कि जो अमोनिया है वो कितना वेपर में प्रेजेंट है वो कितना लिक्विड है
क्यों नहीं?
तो एक ही सबसेट है बट वो लेट्स से अमोनिया एंड वाटर सो दोनों का पता है कि दोनों का मिला के वेपर कितना है इसलिए एक ही ओके
Only one, ammonia. We will be discussing only about ammonia. Water as it is. Water का मेरे पास कोई टेम्परेचर कुछ नहीं है.
तो फिर लिवर को लगा के उसमें जो वहां से वेपर आएगा वो सिर्फ अमोनिया वेपर आएगा
Of course. दूसरा कौन सा वेपर है ही नहीं. वाटर तो वाटर फेज में, लेट्स से लिक्विड फेज में, और इन स्टीम. व्हाई आई शुड वरी? मेरे को नहीं आता होटल साइंस. मैं थर्मोडायनामिक्स.
सर बस यही है सर बस लिक्विड गैस में सॉलिड लिक्विड होता है
हाँ.
और उसमें सर जो बाइनरी फेज मिक्सचर करता है उसमें जब वो मिक्सचर जब मेल्ट
वी आर टॉकिंग अबाउट आयन कार्बन डायग्राम.
सिमिलर इसमें सर दो फेजेस एक साथ एग्जिस्ट करते हैं और एक कन्वर्ट हो रहा होगा सॉलिड में कन्वर्ट होगा लिक्विड दोनों भी
सेम ही है ना.
हां सर मैं वही वेपर में फिर वाटर पे एग्जिस्ट करेगा ना सर वो भी
तो है ना. मैंने कब बोला ना है. लेट्स से हियर इट इज. So 50% of vapor, 50% liquid.
हम डील कर रहे हैं अमोनिया वेपर का निकालना है 1 माइनस कर देंगे
किसकी वेपर भाई? अमोनिया की वेपर ना.
ये है अमोनिया का वेपर
हाँ.
और अगर हमें वाटर का जानना है
वाटर का चार्ट बनाओ. कंसंट्रेशन x for water.
माइनस करके भी आ जाएगा
The concentration is totally different.
बट यहां पे एट पॉइंट x यू हैव ओनली अमोनिया
Concentration x is for any one component.
we don't have to worry about water so it is below the condensation
Of course not. Why I should worry about water? Water का जो होता है
then rather two lines one is for first component having concentration x and other is for other component
one component.
rather two lines
एक सांगतो ना. One component starts boiling over here. The second component is free to absorb the heat, so temperature increases while changing the phase of the ammonia itself. What is the if I supply some x amount of heat? What is the guarantee that only ammonia will absorb? Why not water would absorb? So that is why whatever is that partial part, some x dash taken by ammonia, what will happen? Phase change. Remaining by water, what will happen? Sensible. Temperature increase. So your y-axis is temperature. That is increasing.
so what is the upper line
Ammonia ends. Phase change ends. Entire liquid to entire vapor.
after if you go about it should be partial ammonia in vapor and partial
Ammonia in vapor and liquid. And entire ammonia, liquid to vapor, 5. Nothing related to water. Your chart is prepared in terms of the concentration of ammonia only.
basically the loop will indicate we have both the phases present gas and liquid
Of ammonia,
ammonia
of only one component. Water का कोई लेना देना नहीं. If you want to deal with water, you have to modify the chart for water with the concentration of ammonia. You prepare the chart for concentration of water.
because we got that black line was usually the starting of boiling point of
Boiling point of?
water.
No. It is only for one particular component. Water के केस में pure substance water, single component, क्या होता था? 1 atmosphere 100 degree Celsius. Pressure constant, temperature constant. Here why temperature would remain constant? One particular component is changing the phase. The second component is free to absorb the heat. See, since it is a sensible one, there will be sensible temperature rise. जब pure water था, single component, so we call it as latent part. Now it is a mixture, binary minimum. So let's say component A latent heat absorption. There is no such restriction for component B. Component B, sensible absorption. So overall mixture of the temperature has to change. Why mixture temperature would remain constant? What is the restriction? Keep सारी की सारी heat ammonia ही ले लेगा. Water also can absorb. Are you getting it? Online class.
Yes, sir.
So, conclusion, binary mixture does not have any single boiling point. We cannot specify one particular temperature as a boiling mixture of ammonia and water. That's impossible. Correct? We have seen latent plus sensible. Latent for one component, sensible for other component. So it can have any value. And as you change the concentration, again that temperature differs. Correct? And binary mixtures only will remain in equilibrium for a given concentration. What I'm trying to say is this phase change, that means distance 2 to 5. Whatever is the corresponding temperature, correct? T5 minus T2 is valid for a particular concentration. You change the concentration, 2 dash and 5 dash different. When the concentration would be 0, there is no difference. When the concentration would be 1, there is no difference. 2 and 5. You change the concentration, 2 dash, 5 dash. When the concentration is 0, 2 and 5 same. When the concentration is 1, 2 and 5 same. Correct? Fine. Huh? Here. Yes, you can say it as boiling condensation, it remains same, no? Because no other substance itself is present. So this, you can say boiling point of one component, this is boiling point of the other. Fine. So I say in the conclusion that the equilibrium is a very strong function of the concentration. You change the concentration, equilibrium changes. Equilibrium is the distance between 2 and 5. It is a very strong function of x. You change from x to x dash, 2 will go to 2 dash, 5 will go to 5 dash, different pair. You go to x double dash, 2 double dash, 5 double dash, another pair, and likewise. Clear? Any doubt? Online class?
Sir, can you explain 3 and 4 point again?
What do you want?
3 and 4 point
What
explanation.
do you want?
Not that
You
entire
have to
part.
tell me what you have not understood so that I can explain from that perspective. If I repeat the same thing again, you will still not understand anything. Do you agree? आपको
Yes,
क्या
sir.
समझा नहीं वो बोलो.
How you plotted the third point?
You reach to this point. Any problem? Any intermediate point? Any intermediate point on line 2 to 5. Let's say I reach over here. Any problem to you?
No, sir.
How you will get to this particular point? By reading the temperature. Very easy. So T2 and let's say this point X. Tx are different. Do you agree?
Yes, sir.
So you add the heat at point 2, that means at the temperature T2, there will be phase change, let's say for ammonia, one component. You add further heat, temperature will increase. Ammonia is changing phase, but the other substance is free to absorb the heat, so temperature changes, it reaches to this point in X, Tx. Do you agree?
Yes, sir.
Now, whatever is this heat addition above 2 will have corresponding value of the volumes or masses, whatever. Density से multiply करो तो मिल जाएगा. Volume or masses of the two phases, that is liquid and vapor of ammonia. Do you agree?
Can you repeat?
अरे भाई आप बोलो कि आपको क्या नहीं समझा. Please don't tell me just to repeat.
No, this point only. 2 means 2 phases point.
मैं आपको हिंदी में समझाता हूँ. आपने हीट ऐड किया, सर्टन हीट अमोनिया ने ले ली, सर्टन हीट वाटर ने ले ली. अमोनिया का वाटर एंड वेपर आप कैसे फाइंड आउट करोगे? आपको वैल्यूज चाहिए तो वैल्यू बताते हैं. चलो, let's say this temperature T2 is some 100 degrees. Okay, this is some 200 degrees Celsius. I reach to 150 degrees Celsius. I can very easily measure it. Do you agree?
Yes, sir.
अब 150 डिग्रीज पे कितना वेपर है, कितना वाटर, कितना लिक्विड है अमोनिया का, आप कैसे फाइंड आउट करोगे?
Lever rule by sir.
Exactly. So how would you plot that lever rule? हॉरिजॉन्टल लाइन बना दी, एक पॉइंट आ गया 3 which is on boiling line, रेड कलर, एक पॉइंट आ गया 4 which is on condensation line.
Yes, sir.
Now you have the entire distance 3 to 4. Your concentration has not changed. Your mixture concentration जो भी अमोनिया है in water, okay, उसका concentration थोड़ी change हुआ है. It's just changing the phase. Why concentration will change? So that concentration is as same as x2 and x5 and this x क्या point का क्या नाम दिया गया? Let's say point P. So xp, x2 equal to xp equal to x5. Do you agree?
Yes, sir.
So the total concentration is the same, but the amount of the vapor and amount of liquid you don't know at 150 degrees Celsius. So you plot this as the lever rule and you find out इसको point को क्या बोला है P. So P3 divided by 3, 4. That will give you vapor. Do you agree?
Yes, sir.
And P4 divided by 3, 4. That will give you liquid.
Yes.
Now tell me what is the doubt.
No, sir. Clear.
So eventually ये 3 भी यहाँ से स्टार्ट होके लेफ्ट में ही जाने वाला है, ये 4 भी यहाँ से स्टार्ट होके लेफ्ट में ही जाने वाला है. So ultimately you start from same x2, ये इधर इधर जाएगा और ये 4 भी इधर इधर आएगा. Ultimately you end up at the same x5 and x2 x5 are same. So what is changing is only the concentration of the vapor in bracket 0.3 and liquid in bracket 0.4. The mixture concentration is same. Still any doubt?
No, sir.
हाँ, ऑफलाइन क्लास आपको ठीक है, समझ में आ गया? So this equilibrium, that means 2 to 5. Phase change of one component, second as it is the very strong function of the concentration. If you change the concentration, your 2 and 5 will get shifted. Do you agree? Any doubt, anyone? Now what I want as far as the refrigeration is concerned is not temperature but enthalpy. So what we have done over here is this latent heat HFG for component A, and over here HFG for component B. Boiling point of component A, boiling point of component B. Okay. So instead of temperature, now I can shift it as the enthalpy. And latent heat of component A, no. Latent heat of component B, no. Okay. So I transform the temperature axis y this way and this way also, from temperature to the enthalpy value. And why? Because I need enthalpy only. Refrigeration effect. I will calculate everything comes So this entire chart now equilibrium boiling lines as they are, equilibrium condensation lines as they are. Okay. The temperature lines now got shifted as the isotherms. These are the isotherms in the liquid zone. These are the isotherms in the vapor zone. Okay, and you connect it. So this is how you get the isotherm from the liquid phase, to phase, and vapor phase. Fine. Let's take any random value. 90 degrees Celsius. This is the 90 degrees Celsius liquid phase, 90 degrees Celsius in two phase, and 90 degrees Celsius vapor phase. So the basic structure of the chart is the same one, boiling line, condensation. But instead of having one unique point over here in terms of temperature, and one more over here, which correspondingly would be the boiling points of component A and boiling point of component B. Now I have the HFG, and HFG at one particular pressure is known to me for this component A also and this component B also. Right? Let's say HFG of ammonia at 1 bar, ammonia 2 bar, ammonia 3 bar. Right? And here water. So water 1 bar, water 2 bar, water 3 bar, whatever it is. So accordingly, I will have this Y1 axis as the HFG for component A and Y2 axis for HFG of component B. And HFG is a finite value, it can never be 0. It will be 0 only at the critical point. Correct? So I can split, I can convert the temperature scale into the enthalpy scale, and that is what I require to solve the numericals. So this chart is called as enthalpy concentration chart or HX chart. So instead of TX chart, we are using HX chart. The logic is same. They converted a TS temperature entropy chart to pH chart, vapor compression cycle. Why I need pH chart? Because I need enthalpy. Same logic. So I need to know the concentration जो x axis पे है उसको नहीं change किया, and I need the enthalpy values. So directly read it from the y axis. Job is done. H1, H2, H3, H4 खत्म. Correct? You are replacing the compressor only. बाकी सब same है. Condenser is same, throttle is same, evaporator is same. So I need the enthalpy values which I can trace directly from the chart. Sorry? No. This line and this line, one particular pressure, you can read it over here. Second line, second pressure. Third line, third pressure, same. Loops. This black line and this red line, either typing gadbad hai. This should be over here, this and this. This black and this red is HFG at pressure P1. Then this would be for pressure P2, maybe P3, P4, and like that. What? Nee, this I am saying as P1 for component B, which is wrong. Typing is क्योंकि इधर P1 for component A दिया होगा, so same component B के लिए हो नहीं सकता. कैसे बराबर? Okay, fine. At the same time. At the same time. So accordingly, this line at P2. Then maybe third line here, third line P3, and like this. So always there will be that loop, but now it is cut loop. Left and right side, what you call image crop. Correct? So left and right hand side is crop. Loop is as it is. And why it is cropped logically. Instead of that last point temperature, I am interested in the enthalpy. मेरे को टेम्परेचर में ज़्यादा इंटरेस्ट नहीं है, एंथैल्पी चाहिए. Why enthalpy? Because I have to solve the numerator. So we successfully transform the temperature axis into enthalpy axis. Fine. Any doubt to anyone? So this is how we use the HX diagram or enthalpy concentration diagram. Any doubt to anyone? Online class? टाइम बोलो टाइम. दूसरा लेक्चर होगा ना मेरे को. हाँ ऑनलाइन क्लास झूठ लेगा क्या? Any doubt?
No, sir.
So this is how the actual HX diagram for the ammonia looks like. So here you say ammonia 0, that means entirely water. Here you say ammonia 1, that means entirely ammonia. And now you can see over here, let's say 100 bar, this as the condensation line. 100 bar, this as the boiling line. And ये जो बीच में है इसको equilibrium construction line बोलते हैं. Why they are used, I will tell you. So basic two lines are the upper condensation line and the lower boiling line. ये जो बीच में 100 bar, that is construction line. वो किस लिए होता है बताते हैं. At least this part clear. Equilibrium condensation lines, equilibrium boiling lines. Is this clear? You are going to use this chart and you are going to solve the numerals. So if the chart itself is not clear, then it is very difficult for you to find out the enthalpy values. So even if you have any doubt, simple doubt, silly doubt, whatever, ask me. And please ask the doubt. Please don't tell me to repeat the stuff, because that doesn't serve any purpose. मैं फिर से same repeat करूँगा, फिर से आपको कुछ समझ में नहीं आएगा. You have to tell me कि आपको कहाँ पे problem है. Then I will explain it from that perspective. Any doubt to anyone? Yes or no? No doubt. No, sir. Either I am a very good teacher or you have not understood. There is no third possibility. Now, if you observe this particular chart, the equilibrium boiling lines at various pressures, as I had said, then not shown over here, but when I will chart, the temperature lines, isotherms, are something like this. So now this gives you a very clear hint that you know the temperature, you know the pressure, you know the if I give you concentration and temperature, read the pressure. If I give you pressure and concentration, read the temperature. Do you agree or not? Hello, am I audible?
Yes, sir. Yes, sir.
Don't write anything on the screen because I am sharing the screen. I cannot get back to your screen if you would be typing something. That is none of my business. I cannot read it. Don't write anything in the chat box. If you want to discuss anything, discuss face to face. I cannot even see the chat box. Any problem to anyone?
No, sir.
Then what was written there in chat box? I could get the intimation, but I am not able to see that. तो 2 बार बजा ना सिग्नल. Anyways, I will see it afterwards. Saturated liquid solution. Now you will find out same logic, pressure and temperature. 1 bar, 100 degrees Celsius, saturation. Correct? So when you find the intersection of the isotherm and the isobar, you will get it as a saturated liquid solution. Do you agree? Simple logic, water wala. Do you agree or not? Eh? What kind of noise was that? Someone said something. अचानक से. Are you getting this? Or you want any repetition?
Yes, sir.
What yes? Repetition.
No, sir, we understood.
Now you get to this particular point, saturated liquid. Now you want to find out saturated vapor phase. Unfortunately, in this region, there are no isotherms given in the standard chart. So how would you find it? For that particular reason, these equilibrium construction lines are made. So what we do, let's say, for example 10 bar. So 10 bar saturated liquid, you want to find out 10 bar saturated vapor. So what you do is 10 bar here to 10 bar here vertical. Say for example. Then 10 bar here, let's say here. 10 bar here to 10 bar here. And that is your saturated vapor point. So for making this particular geometrical construction, these equilibrium construction lines are created. Clear to you? Saturated liquid at same particular pressure. You have to go from what you call this? Boiling, equilibrium boiling line to equilibrium construction line. Same pressure. And equilibrium construction line to equilibrium condensation line, horizontal. And then here what you get is the saturated vapor point, saturated vapor state. And naturally, being the saturated liquid and saturated vapor, that is at the same temperature. Do you agree? For that particular component I am talking about, not the mixture. Saturated liquid ammonia and saturated vapor ammonia, it will be at the same temperature. Temperature of the mixture changes. Ammonia at the same value. Do you agree or not?
Yes, sir. Agreed.
हैं? कौन बोला एंथैल्पी कांस्टेंट? ये कंस्ट्रक्शन लाइन के हेल्प से आई एम गोइंग दिस वे एंड दिस वे टू फाइंड आउट द पॉइंट. एक्चुअल प्रोसेस इज दिस टू दिस. You take one horizontal, one vertical to reach to this point. This is my, let's say, saturated vapor. मला काही दिसत नाही. पुढे या. So over here, saturated liquid, let's say this is saturated vapor. So actual process is this. Hypotenuse. I'm splitting it. Eh? ही चीज. याच लाईनचा व्हर्टिकल कंपोनंट हॉरिझॉन्टल कंपोनंट. That is so difficult. You have to maintain the pressure same, no? Because phase change is taking place at the same pressure. Why it would change? So I do not have that hypotenuse known, so I construct it. पर मुझे पता नहीं है. I do not have any information about the isotherms in the vapor zone in actual chart. जो मैंने यहाँ पे लिखा हुआ है T is equal to constant, not given in the actual chart which I will be sharing with you in the next lecture. So what you have is in isotherms in the liquid zone, not vapor zone. So how you will locate this point? What do you know? It is the same pressure. So what I have done, I have taken the help of the equilibrium construction lines. So let's say 10 bar liquid to 10 bar construction, 10 bar construction to 10 bar vapor, and I will join this. It is just resolving the hypotenuse into sine and cosine function.
सर बट वो तो मेरे को प्लॉट करने में मिलता है बट एक्चुअली मेरा प्रोसेस होगा तो मेरा कांस्टेंट कंसंट्रेशन को फिक्स रहेगा तो प्रोसेस होगा.
हाँ तो
वर्टिकली कम रहेगा
for the mixture. ये vapor concentration, liquid concentration. Mixture concentration is same. Vapor concentration, liquid concentration, 3 and 4.
3 and 4 फाइंड करने.
So this temperature scale, in temperature horizontal, enthalpy white would be same. Latent heat, enthalpy बढ़ेगी ना, temperature same, enthalpy change. We call it as latent heat. So enthalpy is changing, increasing from this enthalpy, liquid enthalpy to vapor enthalpy. So the horizontal line earlier 3 to 4, constant temperature, now gets tilted because enthalpy is changed. Temperature is same, enthalpy is changed. पहला जो चार्ट था that was temperature, so horizontal line. Now this chart is enthalpy. हाँ, but 4 कैसे find out करेंगे?